Network topologies. This is going to be a fun one for us because we can take all the knowledge that we have so far, we're carrying it forward to take a look at some of the practical applications of how to connect devices together, both in the local area network and the wide area network. We're also going to take a look at a couple surprises regarding topology where maybe the topology is physically wired one way, but logically works a different. All that and more coming up in Network Topologies. Let's go. So let's get in the time machine and go back a ways to the 1980s where you and I are working on a computer network. And if you weren't born in the 80s, just imagine with me. And we're going to put together an Ethernet network. We're going to focus on a topology called a bus. And this example is a prime example of a shared bus. What we would do back in those days, we'd have our network interface cards, which would be in PCs, big, huge PCs back in those days. And this network interface card would have a little barrel connector here. And what we'd do is we'd connect a T connector. So the T connectors would basically, you push it in and twist to lock it in place on the little barrel. And then this T connector has two ends on it. So on one end, you'd put a coax cable, which would go to another T connector. And the T connector would go to this. This is PC1, this is PC2. And he would connect here. And then we'd have another coax that goes here, another coax. And then at the end, we had terminators. I am the Terminator. What does that mean? Well, a terminator does exactly what it sounds like. It's the end of something. And here's why. So let me put all my PCs in place. Getting ahead of myself. I'm all excited. Okay, so here's our PCs. So because we're sharing this common network, we're going to operate in something called half duplex. That means that only one person can speak at a time. Why? Because if two people spoke at the same exact time, their signals would run into each other and it'd be a mess. It'd be called a collision. So in the early days, we run at half duplex and we use carrier sensing, multiple access with collision detection. That means we listen to the wire, carrier sensing, before you speak, Mr. PC4, you listen, see if anybody else is talking. Multiple access implies that you have multiple devices on the network, not just one or two, but you have like 3 or 4, the possibility of multiple devices on that same shared network segment. And then collision detection says if PC4 sends and PC1 sends at exactly the same time because they both thought it was clear, they both have the ability to detect a collision. They'll both back off. They'll send a little thing called a jam signal to let everybody know there was an accident, and then they'll retry again when they think it's clear again. So that was the world of half duplex with carrier sensing, multiple access with collision detection. So where are we starting with the bus? It's called a bus topology because we're sharing the bandwidth. Everybody's sharing the same common bus. So if somebody says, oh, we're using a bus topology, I want you to think about everybody sharing the same bandwidth, which is exactly how it was in 10 base 2. So how to solve that? Well, we didn't solve that for a long time, actually, until we got to switches, where we have independent collision domains. But what we did do to solve the problem of if a cable broke here, because the whole network would go down if a single cable came off or was broken, we moved to something called a star topology, which is right here. And with a star topology, it's still Ethernet. It's still half duplex. This is a hub, which we don't use very often anymore because it's still one giant collision domain. We're still sharing all the bandwidth. But now, if we have one physical cable that breaks, this port just basically turns off, isolates itself, and the rest of the devices who are active can still communicate. It's wonderful. They're still both, however, a shared logical bus from a perspective of where the electrons go, where the signals go. It's one shared bus. However, this is physically wired as a bus. And this one down here is physically, I'm going to have you pick it out for me. Physical wired as what? What does it look like? Now, if we had, I'm going to redraw it right here. If this is the hub, and we have all these connections going out to PCs, PC1, PC2, PC3, PC4, PC5, PC6, what is that? That is a star. So that's physically wired as a star. So if somebody says, hey, you know what, we're using a bus topology or a star topology, it doesn't always imply what the logical topology is if that's what the physical implementation is. So what is the concept of a bus? A concept of a bus is we have shared bandwidth, shared medium for all the devices in that one little portion of our network. A physical bus is like 10 base 2, which we're not going to see too much anymore in production. For a physical star, it would be a hub. But you know what? Guess who also uses a physical star? A switch. A switch is also a physical star, except we're not sharing all the bandwidth. We are every individual port. As you'll recall from our switching discussion, every single port is its own dedicated collision domain. And on a switch, because we have dedicated collision domains for every device, we turn off the collision detection and carrier sensing multiple access, and we just tell every device the freeway is wide open. You send whenever you want to, and then a switch at layer 2 can intelligently sort out the frames and make sure the traffic goes to the right places. It has some buffering to make it all transparent to the user. So what have we covered so far? We've identified the concept of a bus where we're all sharing the physical medium, and a star, which is where we have, it looks like a physical star. You have this device, and you have little lines that go out from that. Now, one other item that might be interesting, a little bit of folklore, is that we can also have a ring topology. Now, here's how a ring topology might work. With a ring topology, we could logically have a talking stick. I'll give you an example of token ring. With token ring, which is a technology from the 80s and earlier, we would basically not talk on the network until we were given permission. So the permission would go something like this. We would see this thing called a free token. And if we saw this little signal called a free token, we'd say, oh, free token, it means I can talk. We would flip the token to busy, turn it upside down, if you will, and then we could attach our data to the network, our frame of data, and send it to the next guy. The next guy would see the busy token, so he wouldn't start talking. He would take a look at the contents of that payload. If it wasn't for him, he would continue to forward it, and that would just go ring around the rosy like this. So when this guy gets his packet back, he would then say, oh, great, it's made it all the way around. I'm going to take my data off the network. I'll set the free token to as free again and send that token along so somebody else can talk. So that's token ring. So that's a ring topology. Now, unfortunately, or fortunately, depends on how you look at it, even token ring wasn't wired as a physical ring. Token ring was wired as a star also. They had a thing called a MAU, a multi-station access unit, and cables going out to the PCs. So physically, it was wired as a star also. And that's because of ease. I mean, if we have one cable that breaks or goes down, no problem. The rest of the network can still survive it. So with token ring, we used shielded twisted pair, and the logic would be the token would go out. I'll use a different color. The token would go out to a customer, and if it was free token and he didn't need it, he would send it back in. It would go to the next customer, and like this. So logically, it would operate as a ring, but physically was wired as a star. So there we have bus, which we're all sharing the bandwidth, sharing one common network segment. We have a star, which is how we physically can wire something. Ring is how we operating like token ring logically, but also physically wired as a star. And mesh. Now, a mesh. What is a mesh all about? A mesh could be a full mesh or a partial mesh, and it really has to do with how we connect things together. You know, in retrospect, let's do this. Let's talk about point-to-point and point-to-multipoint, and then that will tie in nicely to mesh. A point-to-point connection is exactly what it sounds like. It's only involving two parties. It starts at one point, and it goes to the other, and that's it. So if I have a wide area network, for example, which is where we typically see point-to-point connections, I've got router 1, and I've got router 2, and they're separated by some huge geography. We're using a wide area network service provider to connect. We would have a circuit that starts here and ends here going through the cloud, and that would be an example of a point-to-point connection. Well, what if we have more than one site? Maybe this is our headquarters site, and we have R3 and R4 and R5, and those are all at different sites, geographically speaking. What we could do is we could have point-to-point connections for every single one. And you know who would like that? our service provider, because they get to charge us for 4 point-to-point connections. So a point-to-point connection, the takeaway from that is it only involves 2 devices, one at the end of every of each of the connect. You have a 1 circuit and 1 device at each end, point left to point right. That's it. So what is point to multipoint? Well, point to multipoint is a great idea for that same scenario where we have the headquarters and they've got 4 sites, 2, 3, and 4, and yet they don't want to have to purchase individual point-to-point circuits, whether they're dedicated leased lines or virtualized. If they don't want to have to manage all those, they could have the service provider do this. They could have this, the headquarters could connect one time and then have the service provider cloud connect here. So with one physical connection, then they could logically create the connections to each site in the cloud. So this is called a point to multipoint. Why? Because it's 1 point here. Before it was 4 points, and it has multi-points out here. So there's 4 points. Think of points of contact, if you will. So this could all be like the 10.1.2.3 or 10.1.2.0/24 network, and we have 5 devices on it, and they're all connected, but it's not a full mesh, which brings up to our next point, the topic of mesh. A full mesh would be this: headquarters site, site 1, 2, 3, and 4, and headquarter goes to 1, to 2, to 3, to 4. 1 goes to 4, 2 goes to 3, 1 goes to 3, 1 goes to 4, and all the other connections that I might be missing. Here we go. There's one more there. There we go. A full mesh is when every device on the network has a direct connection, a point-to-point connection to every other device on the network. Now, it's not too practical or realistic in production networks today, especially on wide area networks, to do a full mesh because it's so darn expensive. But that's what a full mesh is. A full mesh is every single device in the network has a point-to-point connection to every single other device. That's a great way of thinking about it because that's what it is. So what does a corporation do if they want fault tolerance? Here's exactly what here's one thing that we might recommend a customer do, you and I. So if they've got the headquarters site and you've got 1, 2, and 3, 4 other sites, maybe we start off with 2 routers at the headquarters site, 1 and 2. So with our 2 routers, maybe we do this. So we're not full mesh. We don't have site 1 connecting to site 2 and 3 and 4 and vice versa. So every spoke, every branch office has 2 connections to the headquarters site. And maybe the blue is service provider 1 and maybe the red is service provider 2 for fault tolerance. That way if one of our networks, one of our providers fails, we still have our connectivity. But by doing something like this, you know what they call that? They call this a partial mesh. So we don't have full connectivity point-to-point wise between every device and every other device, hence the missing ones here and here and here, but we do have some fault tolerance. So another term for that is actually a hybrid. So a partial mesh or a hybrid approach is simply something less than a full mesh. It's a hybrid. It's a mix of point-to-point, not quite full mesh, but has some fault tolerance built in. You could also, for fault tolerance, I suppose, tie 1 to 4, and that would also supply some fault tolerance in case, you know, some network connectivity broke there. But those are the points. No pun intended. So what have we covered? A bus topology is where we're all sharing the same common bus. I would like you to think of that 10 base 2 with the cable and everybody plugged into the bus with half duplex. The star is when we moved over to hubs. We still had a shared bus, except it was physically wired as a star. Token ring is a logical way of having one device talk after another in a clockwise or counterclockwise fashion, but that also was physically wired as a star. And mesh is a series of point-to-point connections. So if we have everybody connected to every other device, and this is referring to wide area networking usually, we're going to have a full mesh. It's not usually cost efficient, so what we normally do is we have some type of a hybrid where we're a combination of point-to-point or point-to-multi-points, but something less than a full mesh. Now these two right here are really just models, and we should talk about them for a moment. Peer-to-peer versus client-server. What does that mean exactly? Peer-to-peer has gotten a lot of press over the last decade with what it does and how it works, but these are two concepts of how to do networking. In every network, there's going to be somebody who requests a service, and that's called a client. And there's going to be something that provides a service, and that's called a server. Let's talk about some we already know. For example, a device on the internet. When you open up your browser and you expect to get a result, that would be a web server. So a web server is a server that provides web services. If you are going to save a file on a common server at your workplace, a file server would be another example of a type of service that's out there. We could also have, for example, a printing service. You have a shared printer. You print over the network, it goes and somebody gets that data and it goes to a printer and it prints out. That's a printer server that's doing it, or a printing service. So the client would be somebody who requests services, and a server is somebody who delivers them. Now in a peer-to-peer model, the lines become a little bit blurred. And that's because we might have a network. I'll just draw a simple network here with two devices. They could be connected with Ethernet. They could be connected on a switch or a common bus or wireless. It doesn't matter, but they have connectivity. And maybe this one device is sharing its files. So we go to Windows or the Linux operating system or the Macintosh that we're on. We go to file sharing and say, yeah, I want to share my files. And poof, this guy, he now has those files available. That's his hard disk. And he's sharing either a file, a folder, or maybe even the whole hard disk. This person over here, using another operating system on his computer, could go ahead and be a client and could reach out and access those files, assuming he had the correct passwords and permissions that were set up when this guy set them up to be shared. Now, why is that called peer-to-peer? It's called peer-to-peer because these are both intended to be just peer devices, both workstations in this example. So whenever you have a network where you have devices that were intended to be end stations, but yet they start sharing resources, sharing printers or sharing files or sharing whatever with each other, it's now called a peer-to-peer model. Now in a bigger scope on the internet, if somebody is going to share their music off of a computer right here, and somebody else is going to collect that music over here as a client, that would be an example of a peer-to-peer model that's currently in motion. So things like in years gone by, Napster and other applications like that, where we can actually share devices or share content across workstations, would be peer-to-peer networking. What is client-server then? Well, client-server is purpose-built network resources. For example, let's say we have a router and we have a network up here and it's got our servers. So we have email servers, we have a web server and a DNS server and maybe some other services as well. And then we have our clients maybe off of another interface. So hundreds of clients over here that access those resources. So the clients here access the services on the servers themselves. And that's a client-server model. So we have purpose-built servers. Maybe if we go back to our virtualization discussion, maybe we have a giant physical server. We're running ESXi for the hypervisor for virtualization. We have our DNS server virtualized here. We have our web server virtualized here. We have our email server virtualized here. So they're all still physically running as servers or logically running as servers, except we're using physically less hardware to house as a whole. This one box doesn't have to be necessarily as big as three separate boxes because they can share resources. So client-server model is purpose-built servers for serving up resources, file services, web services, email, and so forth. Now this last one on our screen is on the blueprint for Network Plus, and I was just like wondering, how in the world did that get there? But the good news is that you and I get to talk about it because it is there. So MPLS, the acronym, stands for Multi-Protocol Label Switching. And there's lots of uses for it. And let's go for an example. Let's say that you and I start a new company and we're going to be a service provider. and we've got lots of routers. So we'll put our routers here. And my question is, now because all these routers are inside of our domain, we're in charge of them, we can connect them any way we want to. We can use Sonnet, we can use Ethernet cabling, we can use any technology that we have interfaces for, we can do. So how do you want to connect these? Do you want to do a mesh? Do you want to do a full mesh or a partial mesh? Let's do a partial mesh. Let's go ahead and connect them like that. Because you know what that would be? That would kind of be a ring. But let's go ahead and do a partial mesh. There we go. So it's not a full mesh, because this router right here, let's put numbers on them, 2, 3, 4, 5. 4 doesn't have a direct connection to 2, and 5 doesn't have a direct connection to 3. So it's a partial mesh. We've got a partial mesh for fault tolerance. That's primarily the reason we do it as well. So across this network, we have some IP networks involved. So we have, for example, maybe this is the 10 network, the 11, the 12, and you and I both know that IP version 4 has 4 octets. I'm just making the short version here. 13 network, 14 network, and the 15 network there, 16, and the 17 networks. We have a whole bunch of networks. And then we have customers that have hired our services. So we have customer connections. And maybe we have one customer called Acme. And this is their site 1. And we have Acme, and this is site 2. So maybe they want to purchase service from us. So now we've totally flipped the cone upside down, because previously when we were talking about the wide area network, we were the customer and we were getting service from a wide area network provider, and now very likely we are the provider. We've got this huge network; it sprawls across the whole country or maybe the whole world. We have the proper interconnections and we're providing services. So Acme at site 1 and Acme at site 2. They want to go ahead and purchase a circuit from us. What kind of circuit do you want to give them? Well, we could do frame relay right here. We could do ATM. We could provide Ethernet right to their doorstep of the building. If we're a cable provider, we could do cable as well, I suppose, if it's there. So the actual last leg of connecting to their gear, to their router, could be pretty straightforward. Maybe they've got DSL and we have a DSL adapter, but we're going to connect to their router. So now the trick is that we want to go ahead and be able to forward traffic between the two sites for them. And so the game is, maybe they've got the 10.1.0.0 network here and the 10.2.0.0 network here. Now, how do we make that happen? How do we provide that connectivity for the customer? And this is a discussion that maybe you can join me later in a service provider CCA level class or a higher level class that we can talk about the details of it in. But the upshot is this. We want to be able to give Acme Site 1 and Acme Site 2 connectivity so they don't even know we're in the middle. We're going to take all their traffic and we're going to forward it, but we are going to make it transparent to them. And we can do it in several methods, but it can appear as, we can make it appear as layer 2. What do you mean, Keith, layer 2? We can make it look like Site 1 and Site 2 are on the same Ethernet network with each other. It's magic, and we're moving all the stuff, but we're talking about MAC addresses. So the MAC address off this interface, layer 2 address, would be seen right here on router 2. So they could peer with each other. They could be neighbors from a routing protocols perspective. It could be great. That's one option. We could also provide layer 3 connectivity. So with layer 3 connectivity, they could peer with us. So they would just see, the Acme router would see our edge router as a network device. They could share routes with us, and this router down here could see us as a neighboring device, and they could share routes with us. So now Acme Site 1 and Acme Site 2 are peering with us, the service provider, at the edge. And they call this a provider edge for that reason. And the customer, you'll never guess, they call it a customer edge for that reason. It's the edge of where the customer meets the provider and where the provider meets the customer. So if they advertise these routes to us, like the 10.1 network and the 10.2 network, we need to somehow take those routes the routing information and advertise that to the far side. So Acme knows to reach 10.1 to go this way, and this site needs to know that to get to 10.2, it should go that way. So there's a lot of really amazing stuff that can happen, but on the topic of MPLS, what MPLS is doing, it allows us to create tunnels inside of our network. That's effectively what they are doing. And they're called LSPs, a label switch path through our network. And I'm going to put a different color here. Let me go ahead and I'm using all my colors already. I've got red, blue, turquoise, and pink. Let me go ahead and use pink. So what we could do is we could create these logical tunnels inside of our provider network to actually forward the traffic between the two sites. So traffic from Acme Site 1 that goes to 10.2, we could forward it through this logical tunnel through our network and pop it out at the far side at Acme Site 2. Now what MPLS does for us, it actually does the forwarding in our provider network. So the service provider network, instead of forwarding based on IP packets, which we've normally done in the past, for example, R3 gets a packet, looks at the destination IP address, forwards it to the next router, who looks at the IP address, who forwards it to the next router, all the way through the network. Instead of doing that, we can actually forward the packet across this label switched path, and the forwarding is no longer done inside of our provider network based on IP addresses, but rather on labels. So we're making label switching decisions, label forwarding decisions, and we can have logical tunnels inside of our network, and it makes the process a little bit faster than doing the IP lookups. But the real benefit of MPLS is a whole variety of MPLS applications, such as layer 3 VPNs, pseudo wires, and a whole bunch of other really cool things that we could do once we have the network in place and up functional. So in this lesson, on this video, on media and topologies and describing network topologies, we've identified, and I'm not sure how MPLS even got in there, because other than being a tunnel, a path across an existing network, it's not really a topology all by itself. But we've covered the bus and how it operates with a shared bus that everybody rides together. It's like everybody's sharing the media on 10base2 and on hubs. With token ring, it's physically wired as a star, but logically it works as a ring. The star could refer to either hubs or switches, and token ring as physically wired as a star with a central hub or switch in the middle with everything sprawling out from that, physically looking like a star. A mesh is a collection of point-to-point connections. A full mesh would be every device has its own dedicated connection to every other device. And in a partial mesh, it'd be something like this right here, where we have lots of point-to-point connections and shared connections, but we don't have a full range of motion between every device and every other device with dedicated links. Point-to-point is a circuit that has only two devices on it. That's it. So if you ever have a question about point-to-point network, is it a point-to-point, yes or no, ask yourself, how many devices could possibly operate on this network? And to say that too, I just want to point out one little caveat here. So let's say this is your Ethernet network. Ethernet. So we're a switch or a hub connecting, and you have two devices here. Is that a point-to-point network? And before you answer, let me give you a heads up. The technology is what we're focused on, not exactly how many devices are there. So if the answer is, well, there's only two devices, but I could certainly add a third. If it's a hub, I could just add a third device or a fourth device. If you can add more devices like that, then it's a multi-access network. It's not a point-to-point technology. So if we bring our example up of R2 in Las Vegas, Nevada, and we have R3 in Reno, Nevada, and we're using a wide area network provider, and we have a serial interface on both sides going to the service provider, that is a point-to-point connection because it doesn't support a third device. So it's the technology behind the scenes that helps drive the type of topology that we're looking at. So point-to-point is two devices max, and point-to-multipoint would be 3+. Can support 3+ if you wanted to. And point-to-multipoint is usually used with headquarters, and then with its connections out to site 1, site 2, site 3, site 4. In this example, it's a point-to-point repeated 4 times. So if we wanted to do a point-to-multipoint, it would be the headquarters site going out to the cloud, and then from the cloud, site 1, site 2, site 3, site 4, all on the same 10.1 network, for example, and this would be our point-to-multipoint. And you can mix it up. You could have a hybrid environment where you have some devices that are point-to-point, others that are on a point-to-multipoint network, and that's absolutely fine. Peer-to-peer and client-server are simply two types of ways of describing network services. Peer-to-peer is where one device, typically being used as a workstation, also is providing network services, and a client-server model is you have dedicated servers, that's all they do for a living is be a server, and you have clients accessing resources. And then we did the finish up with the concept of multi-protocol label switching, which is a way of building overlays and forwarding traffic in our networks on doing it on other than just IP addresses, but by doing it based on labels. I hope this has been informative for you, and I'd like to thank you for viewing.